So we are going to discuss the control hazards today. The control hazards are the most difficult type of hazards arising from normal operation of a program. So the most common type of control hazard is the branch instruction. Branch instructions. So this branch instructions, which has two alternative results. One is this branch instruction. One is jump to the branch target address. Jump to the branch target address if the instruction succeeds. If the instruction succeeds, and second one is the second result we say, or we can say that, or it can execute the instruction after the branch that is we can say at your PC plus 4 of instruction memory, your instruction memory. So if the branch fails, the branch fails. So these are two, as we said. The most common type of control hazard is your branch instruction, which is having two results. In this branch instruction, which is having two results. One is jump to the branch target address if the instruction succeeds, or execute the instruction after the branch at PC plus 4 of your instruction memory if the branch fails. So the problem with the branch instruction is that we usually do not know which result will occur. That is, whether or not the branch will be taken from these two. We are not sure that whether the branch, whether or not the branch will be taken. The branch will be taken. So that we usually do not know, as said, which result will occur until the branch condition is computed. So often the branch condition depends on the result of the preceding instruction. So we cannot pre-compute the branch condition to find out whether or not the branch will be taken. So if you recall that in our instruction execution stages, the first stage is your instruction fetching stage, and after that it entered into your instruction decode stage, and then the register fetching will be done. So in this register fetching, if you recall that, first they calculate the effective address in the execution, or effective address, and once effective address is calculated, then your branch will be complete. if you recall these stages. So then we don't know until this execution stage, or when it is computed, the effective address, whether the same branch will be taken, or it goes to the it may goes to your jump to the target address, or the within the branch the instructions will be taken, is unknown. So from that case, there are certain strategies which are employed in resolving the control dependencies due to these branch instructions. So as said in the control hazard, the control hazards happen when there are PC modifying the instructions, like your jump branch instructions or jump instructions, that this PC modifying instruction that prevent knowing which instruction to execute until the branch target is computed and conditions are checked. So if you recall this branch, the targets are computed at the execution stage, and your program counter will be updated. It will be updated at your memory access stage. So in our previous models, the program counter for the instruction after a branch is only known at the end of your memory stage. So that gives the control hazard. So let me just recall this for you. In our branch instruction data path, when we design, then whatever the ALU output is there, that ALU output is the effective address which is calculated. So that effective address will be given as an input to the multiplexer, and as soon as the instruction is fetched, immediately your program counter is added with 4 bytes. So that we call this as your NPC. So this NPC is also given as an input to this multiplexer, whether to run the same branch or other branches. So the program counter is updated at memory stage. So this same branch or next to branch means that is depending upon our the zero register or zero flag register. If the branch condition is matching, suppose when comparing two values, R1 is equal to your R2, or if satisfied, if this is 0, if they are equal to 0 or not. If it is 0 means the branch will be taken. That means your NPC will be taken. For branch instruction, the program counter is set to the NPC. If it is 0, that means that branch, whatever branch is there in that branch, the next instructions will be executed. If it is not 0, the ALU output which is not 0, then that is based on your 0 flag. If the target address will be calculated, and that target address comes from your effective address, and from that target address, let us see it L1, and the instructions after that will be, so these will be skipped and these instructions will be executed sequentially. So here the problem is in this control hazard, whether this branch will be taken or not taken or not. That is a question that leads to the hazard part. Okay, so this branch may be your conditional branch or your unconditional branch. So at what stage? After ALU. After ALU means before that you are having the execution stage here in this case. So in this execution stage, your ALU is computing the effective address, So until the effective address is calculated, we don't know whether that branch will be taken or not. So that's the meaning here. It says, so the program counter modifies the instructions, and after that your program counter for the instruction after a branch is only known at the memory stage, because your program counter will be updated here. Your program counter will be updated here, right? So now see here, the branch instructions that prevent the issue of the next instruction as a control hazard, that prevents the issue of the next instruction until your memory stage is successfully completes, or essentially the pipeline is stalled until your program counter is executed. So let us see, if you see here, if we have the branch instruction and branch target is there, then it simply says that in control hazard, it says that, if I have the instruction 1, your instruction 2, your instruction 3, let me just write here. Suppose I have the memory. In that memory, I'm having the instructions like instruction 1, instruction 2, instruction 3, instruction 4, and so up to instruction n. This instruction is there in the instruction memory, and these instructions will be stored at certain address like 1000, every 4 bytes, 1008. Fourth instruction is 1012, and so. If this instruction is multiplied with n into 4 bytes. So generally what happens, as soon as if the program counter holds the address of your instruction, the first instruction 1 is at your address 1000, then the program counter gives the signals to your instruction memory that fetch the instruction in the first cycle. It gives that the fetch the instruction. So instruction 1 is fetched. Instruction 1 will be fetched in cycle 1, or instruction fetching, we say IF1. Then as soon as this instruction is fetched, okay, so immediately this address will be, the program counter will be updated with the next address, that is PC plus 4. So next address is 104. So it is going to store 1004. So at the second cycle, your instruction will be entered into instruction decoding, and at every cycle, one instruction will be fetched if it is in the memory. So your instruction 2 will be fetched at cycle 2. At the third, as soon as the instruction 2 is fetched, your program counter will be automatically updated to the next address 1008. In that, at the third cycle, your instruction 3 will be fetched. Instruction 3 will be fetched, okay, and your second instruction will enter into your instruction decoding stage. Third one enter into your instruction execution stage. Sorry, the first one entered into instruction execution stage. Okay, so at the fourth cycle, as soon as your third instruction is fetched, it will goes to the program counter will automatically increase to next address, that is 1012. The fourth instruction. So the fourth instruction will be fetched here. Third instruction will get into your instruction decoding stage. And the second one entered into the instruction execution stage, and your first one get into your memory execution, the memory stage. So at this stage, your instruction 1 is going to calculate or update the program counter with the effective address if it is a branch instruction. So this process complete. But we don't know whether the instruction 2, instruction 3, instruction 4 should be taken or not. For that, as soon as when it enters into instruction decoding, first instruction, when it branch instruction enters into decoding, at the decoding stage only it comes to know that the instruction is branch instruction. So that at that point, when it enters into as soon as it enters into your branch instruction, and it indicates that it is a branch instruction. One is a branch instruction. Your branch instruction, it it stops doing the instruction fetching of your remaining instructions. It stops executing or fetching those instructions until your program counter is going to be updated. So at what stage program counter is updated means in fourth cycle in the memory stage. So until the effective address is calculated, no instructions will be allowed. So that's why from second cycle onwards, it will install all the giving instructions to the instruction fetching one. So there are three bubbles we used here. These three bubbles required before next instruction is issued until the program counter is updated. So this is a control hazard kind of a problem. So how to overcome from this problem? Okay, so if we see this, as we observe that in every stage, we are going to maintain the what you call interstage buffers. So in the first stage, you are finding that instruction fetching and your instruction decoding buffers will be there, and next you will find the in the instruction decode you will have the register file, and because here the registers will be read, and then it goes to next stage. So there you will find the instruction decode stage buffer and your execution stage interstage buffer, and then it goes to the next stage. Interstage buffers are your execution interstage buffer and your what you call the memory buffer. So here you are having the ALU, okay, that is going to calculate the effective address, your effective address here. So that calculated effective address is available. That value, effective address value, is available in this interstage buffer. Okay, so this is your instruction decoding phase and your execution phase. Then it entered into your memory phase, and then from memory phase and write back. So memory and your write back interstage buffers are there. So here your program counter will be updated. It will update here. Okay, update here. Right. So until this, it is these all the next instruction is just stopped until the effective address is calculated. So that's the problem. The branch instruction prevents the issue of the next instruction until memory stage, that known as your control hazards. So how to overcome from this problem? The first one is the fast branch resolution solution. The branch resolution. So in fast branch resolution, what it says that in our case, in this pipeline, if you recall the pipeline architecture, we currently assume that the branch condition is evaluated in stage 3. As we saw, the branch condition is evaluated at stage 3 in the execution stage, right? So in this execution stage, that means we have the what you call the values in between your ID stage and execution stage. When the data is read, the decoded, when the instruction is decoded, then in the whatever the conditional values are there, suppose if conditions are there, so that condition value will be stored in the register, and which is available in the interstage buffer. There itself we know whether here itself the comparison will be done. So in the branch, the fast branch resolution means whatever the condition value is there, you just add the extra adder, or we call the register, to the ID stage to compute the branch target. That means your condition value, if condition value or whatever condition that you are giving. So if you add the additional component at the instruction decoding only, the condition, then that will give the branch target whether same branch will be taken or the other branch will be taken. Right. So here we just assume that the branch condition is evaluated in stage 3 of the pipeline. If we move the branch evaluation up one stage in instruction decoding and put the special circuitry in the instruction decode stage or in the second stage itself, whatever evaluation is happening, if you put in the second stage itself, in the second stage on whatever the ALU that we are using, if the same ALU is shifted one position to your previous stage, then that address will be, the comparison address will be calculated here, the conditional address will be calculated here, right? For one solution. So if you move this branch evaluation up one stage into your instruction decoding, then we can evaluate the branch condition for the branch equal instructions. So this would allow us to take the branch in the execution instead of your memory, because as this hardware is moving to this place, automatically the effective address is calculated here. So in the execution stage only, we can know that the program counter will be updated, because it will also shift one stage to the left. So this would allow us to take the branch in execution instead of your memory, since we would have ready for stage 3, the execution, the 0 output of your comparator that would normally be computed in execution. So the hardware needed to compute equality is mainly a series of parallel XNOR gates and the other gates together, then it will be inverted. So the advantage of this technique is that only one instruction needs to be discarded rather than two more instructions. So this reduces the hardware cost and time required to flush the pipeline. So that is one solution, as it says. So only works this what you call solution, the fast branch solution only works for only the conditional jumps just compared to only 0. So only comparison operation will be done. So no other calculation, addition, subtraction calculations will be done. In that case, it may work. But for some conditional jumps in Cisco instruction set architecture that requires comparing two registers, like we have seen our examples also in instruction set architecture design. We have seen if R1 is equal to your R2, equal to your R2. So we don't know what is the content inside this R1, what is the content in R2, we don't know that much. So when there are two comparisons are there, means when two registers are read, in that case, it is difficult to go with your fast branch solution. So the comparison can be slowed down. Okay. So, but if there is no comparison, then we just put the branch handling logic in the instruction decode cycle only. So in that, it just compares whether R1 is equal to 0 or not. So here only we can know. So only one stall is required, and if it is 0, then the same branch will be taken. If not 0, immediately next branch will be taken, and first instruction will go on executing, and in the second cycle only we comes to know that whether the same branch will be taken or not. If next branch will be taken, means branch target will be calculated. So next instruction target address will be given. So next instruction will start executing. So putting the branch handling logic in the instruction decode that reduce the bubbles to 1 instead of, in this case, it is taking 3 bubbles. So if you shift this hardware for simple comparison in instruction decoding part, then these 2 bubbles will be removed. Another solution is the second solution for this handling this control hazard is assume not taken. Okay. So in this assume not taken, as we saw, we can insert stalls until we find out whether or not branch is taken, right? So, however, this slows the pipeline, in this case, whether we don't know, so we start, we just stall in all these cases. So, this simply shows that uh, the performance will be slowed down, or this slows the pipeline execution unacceptably. So a common alternative to stalling is to continue execution of the instruction stream as though the branch was not taken. So the intervening instructions between the branch and its target are then executed. So if the branch is not taken, this is not a harmful or disrupt technique. However, if the branch is taken, then we must discard the results of the instructions executed after the branch statement. So this is done by using flushing, at instruction fetching, instruction decoding, and instruction execution stages of the pipeline for the discarding instructions. So execution continues uninterrupted after the branch target. So in this case, we just always assume the branch is not taken. So the next sequential instruction should be executed. If this assumption is correct, there is no delay in the pipeline, right? So we saw, let me give you the example. Suppose we have the instruction memory, which is holding the instruction 1, your instruction 2, instruction 3, instruction 4, and this continues. Suppose instruction n is there, and we have just the address will be 1001004 bytes, then 1008 byte, 1012, and so continue. And we have seen that the program counter holds the address of your first instruction 100. Okay, so assume that the instruction 1 is your branch instruction. Okay, so now whether this branch is taken or not taken, that is, that will be known at your memory stage. Okay, that is, but in our case, we are assuming that not taken. Okay, we are assuming that not taken. In that case, how these instructions will be executed? So program counter is holding the 100. That means in the first cycle, your instruction fetching will be done. First instruction will be done. So as soon as first instruction is fetched, so it will be program counter automatically increase to 1004, the next instruction. So in the second cycle, your second instruction will be fetched, instruction 2 is fetched, and instruction 1 will enter into your instruction decoding. Okay, as second instruction is fetched, automatically your program counter will be increased to 1008, next address. So in the third cycle, your third instruction is fetched as per your program counter. So instruction 3 is fetched. Instruction 2 will enter into your instruction decoding. Instruction 1 will enter into your execution mode. So that execution of your instruction 1. Right. So this, is continues at the fourth cycle. It will be updated, program counter updated with the next address as soon as it's fetching done. So your first one goes into your memory address. Second one goes into your execution. Third one goes into your instruction decoding, and your program counter automatically increase to 1, 2. So your fourth instruction will be fetched, and this process continues. So at the fifth cycle, okay, at the fifth cycle, instruction 1 goes into a write back. Instruction 2 goes into your this unit is free, so it goes into your memory stage. Third instruction goes into your execution stage, and fourth one enter into instruction decoding stage. But now we know that at the fourth stage, the effective address, the branch effective address, as we are saying, I1 is a branch effective address. We are following that branch is not taken, so the subsequent instructions as per your program counter, it is taken and they started executing, right? So now at this fourth stage, the effective address, the branch effective address is calculated, and that will be update the program counter, as we saw in our previous slide. Also program counter will be updated. So as soon as program counter is updated, and in that case if the branch is taken, that means whatever the subsequent instructions are taken, they should be flushed, they should be removed from your pipeline. They must be removed from your pipeline. All these instructions must be removed from your pipeline. We call removing this part we call as your flush all these instructions and execute the instructions which are there in that branch. In that branch instruction, once that branch is taken, then whatever the sequence of instructions are there in that branch, they will be taken into consideration instead of I1, I2, I3, I4. If these branches are suppose I7, I8, I9, I10 instructions are there, then all these instructions 2, 3, and 4, they will be flushed, and it is going to start executing. After this memory, it start executing the next instruction. Your instruction fetching of your 7 will be done here. Okay, then at the end, instruction fetching of your 8 will be done. Then it goes with instruction fetching 9 will be done. So 10 will be done. Instruction fetching 10th instruction will be done. So these instructions will be they executed next. They start instruction decoding, then execution, then your memory, and then write back. So this will continue instruction decoding, execution. So this process will be continued. So we call this as your as a result, it says that assume not taken. So always assume the branch is not taken and the next sequential instruction is executed. If the assumption is wrong, need to flush the pipeline to scratch all incorrectly issued instructions, like instruction 2, 3, and 4 in our example, instruction 2, 3, and your instruction 4. And the instructions issued before the actual branch status is known as are called your speculative issued instructions. So in speculative issued instructions that cannot write to the registers and memory until the speculation is verified. the speculation is verified. So as we saw in our example, all these instructions will be flushed. Okay, if assumption is wrong, the pipeline needs to flush the scratch all incorrect issued instructions, and then it start executing the next instructions. Start executing the next instruction 7, 8, 9, and 10. As soon as these instructions are executed, again here the branch will be compute the value. And if this is not taken, then the instructions, the next independent instruction like instruction 2, instruction 3, instruction 4 will be executed sequentially. After this, they are going to execute instruction 2, fetching will be done. Then instruction 3 fetching will be done. Instruction 4 fetching will be done. So this process continues. So this is one solution of your assume not to be taken. So then in this, what is the advantage and the disadvantage of this one means, in assume not taken may not help that much to solve this control hazards, but the branch characteristics having on an average, the 67% of conditional branches are taken. 67% of conditional branches are taken, like your loops. They will in that loop, certain instructions will be there and it will go back. So this loop will be continued. So in this, what is happened? The 85% of the backward branches are taken. Once these instructions are finished, then again it go back and check the condition in the loop. It may be for loop or anything, and the same instruction will be taken. Okay, and on an average. And the 60% of your forward branches will be taken, but 85% backward branches will be taken. So for the integer benchmarks of your 14 to 16% of instructions are conditional branches, like loops. So in that, in floating point, 3 to 12% of your conditional branches will be taken. If they are taken, then backward branches will be there, and forward branches will be around 60%. So why? Because most branches are from loops. So that's the reason this condition satisfied. Second one is, why not assume taken? We have assumed that not taken. Why not assume taken means, why not assume taken? So in assume taken means what happens? The branch target is not known when next instruction need to be issued, until this branch target is not known, until it reach to, or it computes the effective address. It compute the effective address in the effective address in the execution stage, and update the program counter in the memory stage, So up to that, as we saw that every instruction, once the branch is decoded, at least 3 cycles of time every instruction should be stalled. So the second, the third way of control hazard solution is branch delay slots. In this branch delay slots, you can see that there are some conditions in programming languages. There are some situations in programming languages that suppose if we have a branch here, So in this branch, let us consider if condition, then execute these instructions, else execute these instructions. So if you see this is a conditional one. Before that, there may be some instructions which are independent of this branch, and there are some instructions after this branch, they are also independent. Let us see, these are some instructions. And these are some instructions which are independent instructions, and these are your dependent instructions. These instructions are depend upon these conditions. Okay, So then find one instruction that will be executed no matter which way the branch goes, whether it goes inside or not. So find these independent instructions and start executing. Start executing. If this branch condition fails, automatically these instructions will be executed. These instructions will be executed. If it is true, if these conditions true, then these instructions will be flushed, and these instructions start executing. So that is, now we don't care which way the branch goes. It is harder basically than it sounds to find the instruction, but what to put in this slot, that is 80% of the time, means the instructions from before the branch, that is independent of your instructions before the branch, independent of these instructions, and instructions that surely will be executed after this branch, after this the branch part, before and after the branch, must be independent from the branch and the taken or non-taken path. So these instructions from taken or not taken path, which are similar to assume not taken or assume taken, and helps if you go the right way, these instructions will be executed. If it goes wrong, then these instructions will be flushed, and the inside these branch instructions will be executed. But this branch delay slots do not help much with today's machine for your external or input output interrupts. Input output interrupts, because these interrupts are more difficult to handle because the order of the instruction changes based on this input output interrupts. Okay. So the third, another solution is branch prediction. So the actual solution for branches in modern processor is predicting whether the branch is taken or predicting what is the branch target address. If it is taken, then what is the target address? Okay. So incorrect prediction still need flushing the pipeline, and we will discuss this branch prediction as a separate topic in detail in the speculative execution lecture series. Okay. So then during this control hazards will also have some kind of exceptions also. Due to exceptions also, these hazards can happen. So how it is, if the instructions are not written clearly or unclearly mentioned, suppose, and there are some exceptions are there, in that case, after instruction fetching, when the instructions are decoding, if it identifies during the execution time there are certain exceptions are there, some exceptions are there, in that case first it is going to handle these exceptions. So until that, when the next instruction, when the instructions are executed, branch instruction is executed in instruction fetching, decoding, when it is entered into your instruction execution stage, the next two instructions which are there inside the branch, they will be taken. But during the execution, when branch instruction is fetching some exceptions, definitely that hardware part, your ALU hardware, which is using to execute, that will be busy with handling this exception. So automatically your instruction 2 and instruction 3 will start stop executing, and in this execution, if you identify the exceptions, means all those instructions will be flushed out. So if there is an exception, the pipeline must be flushed with all instructions in the pipeline scattered, because if this is not solved, then whatever data this is providing to the next subsequent instructions, that will hold. So that is, instructions experiencing exceptions during the execution also cause the control hazards, and for exceptions, the solution is to just flush the pipeline. So the summary of this, hazard solutions, if you see this, in the generic solution for all hazards, what we saw, you just stall or bubble, or you can flush the pipeline. In all hazards, it may be your data hazard, it may be your structural hazard, it may be your the control hazards. So a side note here is the no operations in pipeline instructions are issued, NOP instructions are issued for the stalls, while the instructions were switched to the NOP for your the flushing part. Next, in the structural hazard, what we have observed, there are different ways to handle this structural hazard. One is separate the hardware resources. Separate the hardware resources means we have separated. One is your instruction memory to solve the problem. Another one is your data memory. And to solve with the register hardware process, we use with the register file, we use the time slots. We use the time slots that your lower edge writing, we use the write time slot and your read time slot to solve this register filing. And third solution, we identified that if these are not possible, you can increase the resources, duplicate the resources. Means you can have multiple memories and multiple registers. And in the data hazard case, we have found the solution that bypass or forwarding. So as we said, in the instruction decoding case, we use the interstage buffers, that instruction decoding and your execution interstage buffers are there. So whatever and in the interstage buffer of your instruction decoding, so the instruction fetching, instruction decoding, instruction execution. So here we use instruction decoding and your execution interstage buffers. Here we use instruction fetching and your instruction decoding interstage buffer. So here the register file is there, and in the here we use the ALU and another interstage buffer here, the execution interstage buffer and your memory access buffer. So as we know that in branch instruction, in data hazards, as soon as the ALU calculates the value, then the results will be available here, that will store in the interstage buffer result until it reach to your write back, via your memory access. This interstage buffer value can be forwarded for the next instruction. So we use that bypass these two stages and forward that value for the next instruction, that to solve the data hazard we have seen. Another one is the instruction scheduling. If there are out of order instructions are there, you just schedule those instructions. If there are no dependencies, then dependent instructions take at the last and independent instructions start executing. That is another solution we have seen in one example in the previous slide, that move your R3 with your R2 value. And in that case, if any other instruction is using this R3, suppose instruction 1 is using R3 and instruction 2 is not using suppose this R3 value, then we just swap this into second and this swap to the third stage. So that is out of order instruction solution we have seen. Then the solution for your control hazard, just we have seen that. First one is you move this arithmetic and logic unit or one computational unit, that comparison unit, into your ID stage. In ID stage, from here to your ID stage, so the program counter will be updated in the ID stage only. So that is move the branch logic to the ID stage is one solution we have seen. And assume not taken means that all the subsequent execution will be start, and if the branch is taken, then flushing will be done. If not taken, those instructions will be executed continuously. Continue executing. Third, the branch delay slats, we have separated the independent instructions and your branch instructions too. So if the branch is taken, then the independent instructions are flushed. If branch is not taken, then the independent instructions start continue executing. And the third one is your branch prediction. As we said, we'll discuss this clearly in next lecture. So then, talk about the superscalar. So up to now, we have seen, we have observed that in every cycle, only one instruction will be taken. In every cycle, it may be your instruction fetching, instruction decoding cycle or stage, or your execution stage or memory access stage. Only one instruction is taken. Only one instruction is taken. But in Superscalar, instead of taking only one instruction in every stage, they may take multiple the instructions will be taken, multiple instructions will be taken in every stage or in every segment or in every cycle. In every cycle, that we call your superscalar. So if you see this, in the modern processor, usually have the number of pipeline hardware components, number of pipeline components by following the Moore's law, that you can add multiple hardwares to execute multiple instructions in single cycle. So therefore, the modern processors usually can issue the multiple instructions at each cycle. So usually these superscalars is accompanied with your out of order to ensure there are no independent instructions that can be issued at the same time. So obviously the multi-issue pipelines are more complex to implement and manage, but how they are, you can see in this case, the two in the superscalar, this diagram just shows the superscalar CPU with your two issues. That means two instructions are issued at every cycle. So you can see that there are two instructions are in the fetching cycle, two instructions in in every cycle you will find two instructions in cycle 1, cycle 2, cycle 3, cycle 4, cycle 5. So it is giving the multiple instructions. So ideally, a two-issue superscalar has a CPU, half of your CPU. In single instruction, we have said cycles per instruction, we have seen in previous example, only one instruction will be there. But here it is taking two instructions, two cycles per instruction, two instructions. That means every instruction takes 0.5 cycles, and the instructions per cycle, IPC, instruction per every cycle is 2 here. Okay. So let us see one example, the case study of this multi instructions per cycle, multi-instruction per cycle is your Skylake pipelining, that Intel Skylake pipelining. In this pipelining, it takes maximum 8 issues per core. 8 issues per core. Okay, so here you can see there are 8 issues are there. That is port 0, port 1, your port 2, port 3, port 4, port 5, port 4, port 5, port 6, and your port 7. So total 8 instructions will be issued. 8 instructions can be issued per core, per one cycle in this case. So in this, if you see this, these are your memory access units. Memory access units, they are using the instruction, they are using load and store, and these are your computational, your functional units, your computing functional units. These are your memory access units. So in these computational functional units, you can see different ports are having different, the computational functional unit, like port 6 is having the arithmetic logic, integer ALU operation, integer shift operation, and integer branch operations. Whereas your port 0, if you observe, it is having different functional units to perform different the operations, like the integer ALU, your vector FMA, feature multiplication, vector MU, these vector operations, vector shift operations, division operations, and branch 2 is there. So like this, different functional in every instruction stage, different functional units are there. So by using your Moore's law, as said, the Moore's law, more functional units are added to execute the multiple instructions. So in this case, 8 issues will be there. So 8 ports are there, and the maximum pipe that depends upon, sometimes it may starts with your 4 to 8 instructions. So based on that, the pipeline stages which is used by this Skylake is 14 to 19 pipeline stages. 14 to 19 pipeline stages. For in our previous example, for 4 instruction 1 to instruction 4, we have seen that without with some hazards, we have seen there are 10 cycles. We have seen, and after solving them with the hazards, then it may reduce to your 8 cycles, like that. So this number of stages in the pipeline stages will be varying. Another case study, case study is your IBM Power 9i. In this Power IBM 9, okay, it issues 4 to 8 issues, or 4 to 8 the multiple instructions will be given. So maximum it takes 8 instructions into the fetch stage, and it decodes. In decode stage it can decode 6 instructions. So in the pre-coded one, the L1 cache, that holds the instruction we call instruction memory. From that instruction memory, maximum 8 instructions can be issued in the pipeline. So in this 8 instruction, it will decode the 4 instructions. To execute at most this 8 the instructions, it uses 4 slices. 4 slices. So in this these 4 slices will take 2 inputs. That means maximum 2 instructions will be taken, and it issues so total 8 instructions will be fetched, and it can give the decode part. 6 instructions it will be decode, and it will give 2 different functional units. One memory functional units, another one is your computational functional units. So these are the computational functional units, and these are your the memory functional units, the computational functional units here, and all these 8 instructions, they use the common memory functional units in this case. And this IBM Power 9 is technically more of your SMT, the design than the Superscalar. And it uses the 12 to 16 pipeline stages. 12 to 16 pipeline stages. That means if you maximum issued 8 instructions, then it uses the 16 pipelines. If it is less than that, minimum it may use the 12 pipeline stages to execute the given kind of instructions. So with this, I would like to stop the session.